Look at a dead star sitting quietly in space. It has collapsed down to about the size of Earth, yet it still contains the mass of our entire sun. At this density, a single teaspoon of its material would weigh tons. There is no fire pushing outward anymore. Without nuclear fusion, gravity pulls inward relentlessly. To avoid collapsing completely, the star relies on a totally different set of rules. Inside this crushed core, atoms are packed so tightly that their electrons are forced into an unusual state. According to a rule in quantum mechanics called the Pauli exclusion principle, two electrons cannot occupy the exact same quantum state. As gravity squeezes them together, the rules of physics literally forbid the electrons from packing any tighter. They push back. This creates what physicists call electron degeneracy pressure, an immense outward resistance that requires absolutely zero heat. For decades, the astronomical establishment looked at this quantum rule and concluded that a dead star would remain stable, frozen exactly as it is, forever. But a 19-year-old physicist named Subramanian Chandrasekhar wasn't convinced. While on a sea voyage from India to Cambridge, he started running the equations to see what would happen if one of these dead stars was just a little bit heavier. What he found was unsettling. His math suggested that the most rigid quantum rules in the universe might actually have a breaking point, setting up a terrifying scenario where pure mathematics flatly contradicted human intuition. This animated chart illustrates the core of Chandrasekhar's calculation. The steep line shows the force of gravity. As you add more mass to the star, gravity gets stronger, pulling tighter. To resist that crushing force, the electrons are squeezed further, and they begin moving significantly faster. So the outward quantum pressure rises right alongside it to maintain balance. But there is a ceiling to this resistance. As the electrons are forced to move faster, their speeds approach the speed of light. Here, the laws of relativity take over. Because nothing can exceed light speed, relativity limits how much additional momentum these particles can actually gain. The outward quantum pressure flatlines, but gravity just keeps getting stronger. Chandrasekhar pinpointed the exact point where the pressure drops off, 1.44 times the mass of our sun. At that specific weight, the outward resistance mathematically fails, and unstoppable collapse begins. When Chandrasekhar presented this calculation, the scientific community openly rejected it. The charge was led by Arthur Eddington, seen here, who was one of the most respected astrophysicists in the world. Eddington and his peers thought the conclusion was completely absurd. Human intuition demanded that nature would never allow matter to compress continuously without some unknown force stepping in to stop it. The establishment effectively chose the comfort of a stable, predictable cosmos over the implications of the equations. To prove the math was right, astronomers would need to see a star break in the physical universe. The perfect laboratory to test this limit exists in binary star systems. Here, a dead white dwarf sits in tight orbit with a companion. The dwarf's intense gravity actively cannibalizes its neighbor, stripping away glowing plasma and relentlessly pulling that mass onto its own surface. Astronomers can watch this happen. They measure a slow, steady rise in the white dwarf's mass. The internal density climbs higher and higher, inching dangerously close to that 1.44 solar mass threshold. The precise moment it crosses that boundary, the quantum rules stop protecting the star. It suffers a total structural failure. The core collapses inward so violently that the immense pressure forcefully ignites dormant carbon, triggering a runaway thermonuclear reaction. The star completely tears itself apart. We call this detonation a Type Ia supernova. It is an explosion so brilliantly violent that it can be clearly seen across entirely different galaxies. And every time astronomers calculate the mass of the star right before it exploded, the trigger point perfectly matches the young physicists' universally dismissed math. It proved that reality operates on strict mathematical boundaries. You can exist safely inside the limit, but the second that hidden threshold is crossed, the old rules of physics simply drop away. If a collapsing stellar core is heavy enough to survive the initial detonation, the collapse continues. It crushes right past the electron barrier entirely, forcing protons and electrons to merge together, leaving behind a hyperdense sphere called a neutron star. Pushing the mass even further leads to the ultimate extreme.
gravity becomes so concentrated and intense that it bends space itself, pulling so hard that not even light can escape, a black hole. Today, the calculations made by Subramanian Chandrasekhar on that long voyage are the bedrock of modern astrophysics. Because these supernovae always explode at his exact calculated mass, we now use their consistent brightness to measure extreme distances across the cosmos. It reveals an unsettling fragility to the scale of the cosmos. A dead star at 1.3 solar masses can sit in the dark forever. Add just a fraction more mass, and that eternal calm collapses entirely. The night sky is filled with these peaceful-looking systems. They seem permanent, but many of them are quietly sitting right on the edge of a mathematical limit.